Hey there. All right, so we're going to look at binomial and normal distributions today. Let's start with the binomial distribution. And a distribution is just kind of a graph that shows all the different possibilities. Before we get into the distribution part of this, let's just talk about what a binomial experiment is. So this is some kind of a survey thing that you do that, because they call it a binomial, there's only two possible outcomes. So that's where that term binomial is coming from. Two outcomes, like it's a yes or no question, a true or false, success or failure, Jayhawk or Wildcat. It's one or the other. There's not like 10 options. It's just one or the other, two options. Now, so in a binomial experiment, there's going to be n independent trials. Okay, so to say n independent trials means I'm going to randomly ask a variety number of people. Each trial has only two possible outcomes, so they have to pick one or the other, the true or the false or whatever. And then the probability of success stays the same for each trial, and we'll talk about what that means. And that if the probability of a success we're going to say is p, then to find the probability of a failure, it would just be 1 minus that. So if the probability that it's going to rain is 0.6, the probability it doesn't rain would be 0.4. All right, let's move on. Let's do a binomial experiment. Well, actually, you don't get to do it because you weren't in class, I guess, or maybe you're just watching this for fun. So we did a binomial experiment of KU fans versus K-State fans, and there's, you had to pick. It was one or the other. There's no like, I like Mizzou Tigers. I mean, who likes them? So you had to choose, and because I don't have people to actually ask for this video, I'm going to make my life easy and make nice numbers. I'm going to pretend we did this survey and we got, let's say I asked 10 people, and I'm going to say 8 of them chose a Jayhawk, 2 of them chose Wildcat, for obvious reasons. All right, so the probability of being a Jayhawk fan in that particular set of people would be 0.8, and the probability of being a Wildcat fan in that set of people would be 0.2. Now keep that in mind, we're going to use that over and over. So binomial probability is looking at the probability that you pick someone and they're going to answer however you want. Okay, so like in this example, if I was going to ask 5 people in this set of 10 people, if I'm going to ask 5 of them, what's the probability that exactly 3 of them would choose a success, which for obvious reasons we're going to call is a Jayhawk. And that isn't because there were more of them, it's just because Jayhawks are better. So we're going to look at all the ways that might have happened. So if I'm going to ask 5 people, and I want exactly 3 to say, yeah, I'm a Jayhawk fan. Okay, so it could have gone like this. I could have asked 5 people, and I got 3 Jayhawk fans, and then at the end I got 2 Wildcat fans. Or maybe I had a Wildcat fan at the beginning, and then 2 Jayhawk fans, and then a Wildcat, and then another Jayhawk. Or maybe it was Jayhawk, Wildcat, Jayhawk, Wildcat, Jayhawk. I don't know. A lot of different ways that can happen. So when I do this, I'm going to have to consider all the ways that that might happen. And then what I'm going to do is I'm going to have to look at the probability of that. So let's look at just this first scenario. I'm going to ask somebody randomly, independently, are you a Jayhawk or Wildcat fan? Again, this is in my group of 10. Well, the probability they say Jayhawk is 0.8. And, so I'm going to multiply. The next person I'm going to ask, again, it's independent, so when I ask them randomly, it's still a 0.8 probability that they say Jayhawk. And then the third person, 0.8 probability they say Jayhawk, and then I want them to say Wildcat, then I'd have a 0.2 probability. And then I want another person to say Wildcat, so I'd have another 0.2 probability. This is the probability, then if I multiply that all together, that's the probability of this scenario happening right here. But that's only one situation. This might have happened or this might have happened. So what I have to do is I have to combine these two ideas. I have to look at what are all the ways this can happen, and for each one of those I'm going to have this happening. All right, so this comes up with our formula that we're going to be using. If I want to have the probability of an exact number of successes, again, that's a Jayhawk. Okay, what I have to do is I have to look at all the ways this can happen. So this is going to be combinations of n people, and I'm going to have exactly this many successes. Okay, and so my n people would be my 5 people, and I want 3 successes. So this would be a 5, choose 3. And then what I'm going to look at is, well, what's the probability that they do say Jayhawk? Because that's a success. What's the probability of a success? Well, that was my 0.8. So I'm going to have a 0.8 to the how many of them that I want, which in this case, I wanted 3. So you can see, here's my 0.8 to the 3rd power times the probability that they don't say Jayhawk, which I've decided is a 0.2. And how many of those do I want? Well, I need 2 of them, so that would be my n minus k, 5 minus 3. So it's combining all the ways it can happen, and then what it would look like when it did happen for the probabilities. Let's finish out this problem then. So what this example would look like, the probability, oops, let me get a pen. The probability that I was going to ask 5 people and I get 3 people to say Jayhawk. Well, that would be the combinations of asking 5 people, I want 3 successes. All right, times the probability that I have a success, which is pretty high, it's a 0.8 probability that someone's going to say Jayhawk. And how many of those do I want? I want 3 of them, so it's a 0.8 to the 3rd, times the probability of a failure, that's a wildcat, is 0.2. And how many of those do I want? Well, I want 2 people to say that. And I just typed that in my calculator. And to hurry us along, I've already done that. I end up with a 0.205. That is the probability that I ask 5 people. In that original group of 10, I'm going to ask 5 people, and I want exactly 3 people to say Jayhawk. That's really not a very high probability. And the reason for that is because we're overwhelming Jayhawk fans. So for only 3 people to say that, I would have expected more people to say that. So that's why that's kind of a low probability. Once you get the hang of this little formula, it's super easy to do. So let's just try one more time. It says, so now I'm going to ask 7 people. What's the probability that exactly 2 people choose a success? All right, so I'm going to walk through it. Probability of getting 2 Jayhawks equals combinations of, there's 7 people, I want to end up with 2. Times the probability of somebody saying Jayhawk is 0.8. How many of those do I want? Just 2. Times the probability of a failure, that's a wildcat, 0.2. And how many of those do I want? I want to end up, well, if 2 people are going to say Jayhawk, then I need 5 people to say wildcat. All right, I type it in. All right, I just did that. I got a 0.0043, looks like. Super unlikely that I'm going to get only 2 people to say Jayhawk. Now, this particular scenario, I kind of messed that up because early on when I decided, oh, I'm just going to make my life easy by using easy numbers, and I only had then 10 people, so this scenario couldn't happen because I don't have enough Wildcat fans in my class, in my group of 10. But the setup is the same regardless. All right, so let's practice that with some other stuff other than Jayhawk and Wildcat. Remember, it's a binomial experiment, which means you have 2 options. So here'd be a scenario. Find the probability of having 5 left-handed students in a class of 25 if the probability someone is left-handed is 0.1. Okay, so you're going to set up that same formula. This is going to be probability of getting 5 left-handed people. All right, so combinations of, I've got a group of 25, and I want to end up with 5 successes, 5 left-handed people. The probability of a success, the probability of being left-handed is 0.1, and I want 5 of those, and the probability of being a failure, or I'm sorry, well, you're not a failure, don't get a complex. The probability of being right-handed is 0.9, and how many of those do I want to end up with? Well, I need 20 of those to happen. All right, then we're going to type it in. All right, I end up at a 0.06, I'm going to go with a 0.065 is the likelihood of me picking out exactly 5 people to end up. Now, this one, there would be a lot of possibilities here. You got 25 people, and so I'd have a lot of different scenarios. So to have a specific scenario happen, the likelihood of that's probably typically going to be kind of low. All right, so then what my goal here would be for you to go to your note sheet and practice doing some of those from your assignments and get familiar with that formula. I'm going to go ahead and move on. All right, so now what I'm going to do, when we get to the binomial distribution, okay, all of that stuff was getting us ready for this, which is what the lesson is really about, which is creating a binomial distribution. The distribution shows all the different possibilities that might happen. So looking at this scenario, I'm going back to that original Jayhawk Wildcat, and I'm going to look at all the different ways that might have played out if I ask 5 people and how many successes I might have ended up with. So I'm going to look at the scenario, what if I asked 5 people and nobody said Jayhawk? What if I ask 5 people and 1 person said Jayhawk, or 2 people, or 3, or 4, or 5? Okay, again, some of that won't make sense in that example. Remember that the probability of it happening is what I'm looking at. Forget the fact that there were only 10 people in the room at the beginning. Let's just say there was a big group, and I still ended up with 80% of them liking Jayhawks and 20% of them liking Wildcats. So I'm still going to use my 0.8 and my 0.2, but what's going to change is this combination at the beginning. The probability that I ask this group of 5 people, so that's going to be 5, and I get 0 people for success, 0 Jayhawkers. All right, so then I'm going to take the probability of being a Jayhawker to the 0 power, because I want 0 of those, times the probability that Wildcat fan, and if there's nobody saying Jayhawk, that means 5 people are saying Wildcat. Okay, and I look at that scenario, and I do this for every single one of them. Combination of, I asked 5 people, and now I get 1 Jayhawk fan. All right, that's a 0.8 to the 1, and a 0.2 to the 4. And then we come down and do it again. 5 choose 2, 0.8 to the 2nd, which means 0.2 would have to be to the 3rd. And I keep working my way down. 0.8 to the 3rd would be another, okay, this is the probability I get 3 Jayhawk fans. Okay, this is more likely because remember that there's a lot of Jayhawk fans, that you're more likely to be a Jayhawk fan, so the likelihood of this scenario happening is much better. And I think I'm still going to be even better off down here. Probability that 4 people choose it is 0.8. Oops, undo, to the 4th. And 0.2 to the 1st. And the last one, choose 5 people, all 5 of them say Jayhawk fan, which I can't imagine why that would not be the case, but whatever. All right, so that's what I'm doing. Now I have to do the math on all of those. So let's go do that. I know you're just going to wait for me to do all the math for you, but it would be maybe nice for you to practice doing it on your own. But the other thing is, you might want to get smart about entering this in your calculator. I'm going to do 5 math over to probability, combinations, choose 0, and I'm going to do this all in one shot because I would like to come back and just edit that every time and just tweak and then I don't have to rewrite everything. So I'm going to do 5 choose 0 times 0.8 to the 0 times 0.2 to the 5th. And what I end up when I do that is a very, very small probability. I have a 0.00032. So super unlikely that nobody's going to be a Jayhawk fan. Okay, got that. Now what I'm going to do is I'm going to go through each one of these, but let's go back up. Instead of having to retype that, I'm just going to either arrow up or do second enter, however you can bring that back, and just tweak it to 5 choose 1, 0.8 to the 1, 0.2 to the 4. And this time I get a 0.0064. Are you doing this with me? Are you writing it down? Are you doing something? I'm going to go through all my different possibilities and write them all down. So you can either pause the video and go do that, or just wait for me. You might as well do it yourself. All right, so here are all of my numbers. Sorry, I should have mentioned you needed to write little there. Okay, so what you should happen here, if this is all the different possibilities that could even occur in this scenario, all of those probabilities should add up to 1. Okay, you can look at it and see some things are more likely to happen, some are less likely. The most likely scenario right here is that 4 out of my 5 people. That's a 0.4 probability. That's the most likely scenario. Now to get all 5 people, not all that uncommon either, or the 0.3, but would be very rare for me to have, in this particular scenario, have this few many Jayhawk fans based on that data. Okay, now the distribution is actually the graph of all of these scenarios. So you're going to come over here and you're just going to make yourself a little bar graph. Mine is not going to work awesome, so I'm going to do my best here with just like a highlighter thing and say, all right, so the probability of getting 0 people, well, good grief, that's like non-existent, but I'm going to put like a line of something there just to show, hey, I did at least look into it, okay? 1, also just a hair bigger. And then the probability of 2, okay, that's a little bit bigger. That's like about right here. All right, probability of 3, okay, now I'm up to a 0.2, so that's a little bit more likely here. All right, and the probability of 4, that's right up here. Okay, so that bar is taller. And then 5, I'm back down to a 0.32, somewhere like right there-ish. And that is my binomial distribution. Now, as you look at this, then, this is displaying all the different probabilities. If you look back at your notes on the dice thing, and there was a probability distribution there. Now, that distribution was beautiful. This one, not as beautiful because it is skewed, and I guess that doesn't really matter if it's does that make it not beautiful? I think it's beautiful. If your distribution shows that it's skewed, then it's indicating that these are not equal probabilities, which we knew that going into it. It's just a nice display to kind of a visual of what's the most likely situation going on. Pretty easy to do. It's just a little bit tedious with the work, so get efficient with your calculator on getting those numbers. Now this is skewed because my probabilities were different. What do you think it would look like if I did rolling the dice, or did something that had a little bit more equal likelihood of things happening? All right, now this is the activity that we did in class, which I'll just kind of walk you through real quick. So flipping a coin here. We split it up and everybody got to flip a coin 8 times, and what do you think would be the most likely scenario on a normal coin? You'd think you'd flip it 4 times, and we're doing it 8, so you'd think 4 times head, 4 times tail would be the most likely scenario, that since it's supposed to be a 50-50 thing. But that's not going to happen for everybody. But if we did a huge graph of everybody's 8 coin tosses and what happened here and what happened here and what happened here, ideally we would not get such a skewed distribution, and we would see it more like a very if I was doing my distribution, and I might have, let's see, what did it say here, I don't know, let's say 0 heads, 1 heads, 2 heads, 3, 4, 5, 6, 7, 8, 9. And we would expect a very tall bar right here at 4 heads. We'd think that would be pretty likely, and probably the 3 not as much but close, and 5 should be sort of the same. And then each step as we go out should kind of be a little bit less, a little bit less, a little bit less. Now that didn't make sense. Okay, and so this would not be a skewed distribution. On something that has an equal probability, it should be a nice, beautiful graph. All right, which actually has a name. If you can get a distribution that is not skewed, then what we might call it is normal distribution. A normal distribution is symmetrical, and it has on this we call it a bell-shaped curve. Maybe you've heard of that phrase, a normal distribution curve or a bell-shaped curve. When you ask a teacher to grade on the curve, that's really what that means, is that you should be having like a lot. In fact, what this would mean is you'd have a lot of C's in here in the middle, fewer B's and D's, not so many A's and F's. Okay, so depending on who you are in that group of people, sometimes grading on the curve is nice, sometimes it's not. Really, to you, grading on a curve just means, hey, will you make my grade higher? Which is not really mathematically what's supposed to be going on there. Okay, so let's talk. We're moving on now to the normal distribution curve. The normal distribution curve is something that's going to be symmetrical, and if it truly has a normal distribution, we have this really profound rule name called the 68, 95, 99.7 rule, which says that in a normal distribution, 68% of the data will fall within 1 standard deviation, 95% will fall within 2 standard deviations of the mean, assuming the mean is right here in the middle, and 99.7% will fall within 3 standard deviations of the mean, which means there's a tiny little bit still out here on the tails of the bell-shaped curve because we haven't quite hit 100% within that 3 standard deviation range. Now, I'm not sure how much you've seen. Some of you probably have seen normal distribution curves. Some of you have not. So I'm going to kind of go with it like you have not seen normal distribution curve. Now, before we get into really working through one, let's talk about just some details. It is called the 68, 95, 99.7 rule, but sometimes people like to, simplify that and break it down bar by bar. So if you have 68% of your data that is supposed to fall within 1 standard deviation of the mean, we'll talk about what that means here in a minute, but if you're supposed to have 68% fall within here, and since it's all symmetrical, what that really means is you'd have 34% here and 34% here. And then let's go to the 95. 95% of the data should fall within 2 standard deviations. So if you look at that and do the 95, and that's not going to divide near as nicely, so what I typically would do on that is I would do, actually there's different ways to do this and different people visualize it differently. What I've always done is I just think, okay, 95% is supposed to fall within here, but I've already used up 68%, so I would take 95 minus the 68, that gets me 27, and divide it evenly between these 2 bars. So however you want to do that, I'm going to end up with 13.5% in each of these bars. And then 99.7% is supposed to fall within 3 standard deviations. So 99.7% should fall, of my data, should fall in that full range there. All right, so if I take the 99.7 and I subtract the 95 that I've already used up, now I have 4.7% that I have to divide evenly between both sides. This ends up being, let me get a pen, 2.35% here, 2.35% here, which means out on the tails I have this tiny, tiny little bit left from the 99.7 that I've used up. I'd have 0.3 left for all of it, split evenly. This is a 0.15% of the data should fall way out there on the tails. Now, if you just want to remember this, and you can kind of think through the math on finding how many are in, or what percent would fall here, or maybe what percent would fall from here to here, where you have to kind of think through some things. But if you're like I like to memorize stuff, and you want to remember all those columns, you can do that too. You do what works for you. Now let's talk about what that standard deviation means. When we talk about it needs to fall within one standard deviation. Okay, here's how this works. You've got some, let's just say these are quiz grades. Okay, so you have all these quiz grades, and I'm going to try to keep it a low number of people. I don't even know how many there is here, but I have all these quiz grades. What I would do with those is I'd find the average, or the mean. This is called X bar. You can see there's a tiny little bar above there. X bar is the mean. That's a statistics thing. So I'm going to find the mean. And then what I do is I take whatever the quiz score and I subtract the mean from it. So I'm looking at how far off from the mean are we, and I do that for each person. And then I take those numbers after I've decided how far off from the mean they are, and I square them. So I'd square each one of these numbers and fill in this column, and then I look at the average of those. Now by squaring them, what I'm able to do, I don't know, there's mathematical stuff behind it, but when you square it, now everything's going to be positive, so it's not going to like cancel out, because you got some positives, you got some negatives, things cancel out. So if you square them, now they're all positive, and then I'm going to find the mean of all of those squared values. And then, because I want to get back to before I squared it, I take the square root of those, of that mean. All right, that right there is your standard deviation. So you're looking at how far do your quiz grades deviate from the class average. You know, is there a wide variation? Like, or do we all do about the same and we're all close to the mean? That it shows you kind of the spread of the scores. How far spread out is it? So if they were very spread out, you'd have a normal, assuming it was normally distributed, you'd have this bell-shaped curve that looks something like this, if they were all spread out scores. But if you had a lot of scores that all clustered around the mean, then your bell-shaped curve would look something like this. And then your bars, like up here, your bars would be a little bit wider. So there's your 68% falls within one, and these would be kind of nice wide bars. But here, when you put the mean in here, the bars would be a lot skinnier because there wasn't as much variation when your quiz scores. So these are both bell-shaped curves. They just look different based on what that standard deviation was. Now we're not going to we're not going to calculate that by hand. I mean, you can if you want. I gave you the formula, so if you want to, you can. But what we're going to do is I'm going to be giving you that information, or we're going to let the calculator figure it. Let's start with one where I just give you this information. So it says, build a normal distribution curve from 30 different, we'll say test values. There's a mean of 18, and the standard deviation is 2. Now this is off to the side. That's just my personal note. I put it off on the sideboard, but let's just draw it right here in your notes. So the first thing you got to do is draw this nice normal bell-shaped curve like this. Kind of spread it out, make it big because you got a lot to write in here. And then I'm going to draw a line across the bottom. That's kind of my baseline. And then I draw the mean right down the middle of this thing. The mean falls right here. It's 18. And now I'm going to draw my 3 bars, and I want to go 1, 2, 3, and still have a little bit of a tail. Do it the same on the other side. And then I'm going to put my scale on here with my standard deviation. So if the mean is 18, then I'm going to go up 1 standard deviation. That would take me to 20. Another standard deviation would be 22, and then up to 24. Let's go down a standard deviation. That would take me to 16 and 14 and 12 because the standard deviation was 2. And this is what I've got. Now as you're looking at it, I kind of combined a couple different things here. I went ahead and redid our bell-shaped curve we just drew, and then I put the percents in. Now you're not going to do that. I just needed to do it for the video. You have your bell-shaped curve drawn. That's what you want. Now look back at that, and then we're going to answer these questions. It says, what percent of the data is greater than 18? Well, looking at that, 18 falls right here. What percent of the data is over here? Well, remember, it's all symmetrical. The mean cuts it right in half. So that should be 50%. Now, I can add these all up, but I'm not going to bother because I know that's 50% of my data. So 50% should fall above 18. Next question. What percent falls between 16 and 18? Okay, right here, that's this bar. Now, if you already have it broken down, then your life's pretty easy here if you remember all these different numbers. Otherwise, you'd remember this is 68, and this bar would be half of that, so it's 34. 34% of my quiz scores should fall between a 16 and 18. Okay, what percent should be greater than 24? So I look at my graph and I say, 24 is right here. That's just the tail. How much of the tail? Well, 99.7 was here, which means 0.3 is left in the tails, and I'm just looking at the upper tail. So 0.15% of my quizzes should fall there. And the last one, see if you can figure that out. What percent is at least 14? All right, at least 14 would be all of these. So now don't make your life difficult. Don't start adding all these up. Let's do the opposite. Isn't it easier just to see what's left down here? Well, that's 2.5% is still down here, which means this is everything else. So almost everybody should be at least a 14. All right, so that would be 97.5% should be up there. All right, now, something I guess I kind of skimmed over that I should talk about. There's a lot of things in life that have this normal distribution curve going. Like SAT or ACT scores are typically normally distributed. And ideally, a pre-calc test would be normally distributed. You can kind of see that sometimes on a stem and leaf. If I ever put that up on the board, you can kind of see the curve going on. Typically, we're skewed towards the high end, so that's a good thing, I guess. Maybe my tests are too easy. I need to change that. Okay. But another thing, like how long a battery lasts, or even a light bulb, that's another thing. It typically lasts, the length of time that it lasts is based off of normal distribution curve. They're probably going to advertise on the packaging, oh, it's going to last this many hours. And then you're going to have some that last longer and you're going to have some that last less, but it should look symmetrical on how many of those batteries or light bulbs do that. All right, let's move on to this next column of questions. This is a little bit trickier. It says how many should be greater than 20? Well, not how many, what percent is greater than 20. If you look back at the original problem, I said there were 30 quiz grades. So 30 people took this. How many of them should have something greater than 20? Well, let's look at the percent. First of all, right here, the percent. And again, I like to think through this in my head. I like mental math. I like for you to have mental math. If 50% is here, I'm going to not use the 34% and I have all the rest. So these columns here should add up to, anybody? 16%. Good. Okay. So 16% of 30 people. So what I do then in my calculator is I take 0.16 times 30 and say, oh, 4.8 people. So 4 or 5 people. I'm going to go ahead and just leave my numbers exact, but I would expect then 4 or 5 people to have at least a 20. Okay, how many of my 30 people are going to fall between a 14 and a 20? So the first thing you're going to do is go look at your normal distribution curve. Between a 14 and a 20 are these three columns. This is 68 plus another 13.5. 68 plus 13.5. Why am I going to my calculator? That's terrible. Plus I put times, that's not going to work. Okay, 81.5. You knew that. Okay, 81.5% of 30 people. So then I'm going to take that times 30 people, and I have 24.45. So I'll go ahead and write the exact answer. But I know then that, okay, 24, 25 people should end up in that range. You do the next two. I'm not doing it for you. You got to do it. Come on. I can't do everything. You're supposed to pause the video and go do some math. Geez, I always cave. There it is. That's what you should have gotten. About 4 kids that fall between a 20/22 and a 0.7 kids, so maybe 1 kid falls between that 12 and 14 range. Okay, that's your normal distribution curve. All right, so the last thing we're going to do then is what about, okay, so that's a big part of it will be you having, I'll give you the information, you draw it out. But I wanted to also show you how to do that on your calculator so you're not finding everything the hard way. All right, so we're going to use the data from the standard deviation example problem, so I'll have to go back and look at that. I'm going to show you how to do this on your calculator, how you find the mean, the standard deviation, and create a normal distribution curve. All right, so first thing you're going to have to do is go back to that slide in your notes. I know it's teeny tiny, and look at what were the numbers. What were the test grades or the quiz grades there? Okay, maybe I'm asking too much. As I went back and looked, that's way too tiny. All right, so here's what you've got. I'm going to list out what those numbers were. It was, and we'll call these test grades, there was an 84, a 90, an 80, 76, 84, 88, 80, 84, and 87. This is not going to be a slide where you let me do all the work. You really need to actively be doing this on your calculator with me. First thing you got to do is go enter these into your calculator in your, let's just put them in list 1. So you'll need to pause the video, get your calculator out, and let's put those in. Once you have them in list 1, you can start the video up again. All right, once they're in your list, you're going to go to Stat and Edit. No, I'm sorry. Okay. Stat. Okay, we already edited. Now you're going to go over to Calculate. This is where you would do your linear regression stuff, but we're not doing a linear regression. What you really want is that very first option, one variable statistics. So you click Enter there, and you run your one variable statistics, and right there it gives you all the information you'd ever want about that list of numbers. So the very first thing is X bar. Remember that was your mean, and so the mean looks like it's an 83.7 is what I'm going to round that to. 83.7. Maybe you want to put this notation so you remember that that's X bar. And the standard deviation is, the notation for that is actually a lowercase sigma. It looks like this. So if you look down towards the bottom, you have standard deviation of X. So if we were to do all the math with it, and we found this was the mean, and we wanted to see how far these test scores varied from the mean, the standard deviation would equal 4.16. We'll call that good right there. Maybe I should actually, let's just call it 4.2. Now there's other things there. You can see up at the top after X bar, there's the sigma. Recall that that means the sum. Maybe you don't know that, but we'll talk more about that. Okay, the sum of X. So if I added all these test scores up, that's what it would equal. The sum of the numbers squared. The capital S is a sample standard deviation. All of this stuff is things that you would use in a statistics course. N is the number of test scores that there were. You actually can scroll down, and there's your minimum and your quartile 1, your median, your quartile 3. Does this look familiar? If you were making a box plot, you'd be using those numbers. All right, what we're going to do, though, is all I need is that X bar, the mean, and the standard deviation. And then what we could do is go draw this out. Okay, and then I would put my mean right here in the middle, 83.7. And then I would add 4.2, add another 4.2, add another 4.2. And then I'd go back and I'd subtract 4.2, subtract 4.2, subtract 4. And then I can answer all those same kinds of questions. But I let my calculator find the data, or find those key information for me. the next question says, be able to then, with that information, what percent of the data should fall within one standard deviation? Well, that's 68%, and I can find certain columns out. Be able to do the how many scores would fall, so that's where you have to take your percent times how many there were. Now, how many actually did? Okay, so let's do this with our particular one. That's just saying within one standard deviation, so I can do that. I'm going to get out of that, and let's go ahead and just do 83.7 plus 4.2. All right, so my next column would be 87, I know this is messy, sorry, 87.9. I need that number. And then if I take the 83.7 and subtract my standard deviation, this bar would be 79.5. And so the question is asking what percent of the data should fall within there? Well, we knew 68% should fall, which equates to how many scores? Well, remember there were 9 scores there, so I'm going to take 0.68 times 9. I end up with 6.1, so I'm thinking 6 scores should fall within that. And then the last question here, how many actually do? This is like, all right, did this data really, I mean, I just told you to do the normal distribution. Maybe it was very skewed data. Well, I think I purposely tried to make it look, I mean, we didn't look at a full distribution on it, but it was supposed to be normally distributed. So let's count them up. How many fall between a 79.5, so it's going to have to be an 80, up to an 87.9, so I really have to cut it off at the 87. So somewhere between an 80 and an 87. How many of my scores do? This one does. This one does. This one. This one. This one. Oop, and I get to count that one. How many? Well, that's 6. Well, good grief. There you go. Perfect. 6 of my scores did, and that's what I expected to have happen since it was normally distributed. All right. Homework is to go ahead and work on your worksheet. Have fun.